Hello, in this lecture we'll prove Stewart's theorem in two different methods. In a nutshell, Stewart's theorem yields a relation between the lengths of the sides in the triangle to the length of its Cevian. This is triangle ABC. The length of side AB is equal to 2 units, side AC equals to B units in its length, side BC equals to A units. In addition, line segment BD equals to M units, line segment DC equals to N units, and the Cevian in this triangle ABC, is line segment AD. And the length of the Cevian AD is D units. That is to say, AD equals to D units in its length. So, repeat again that Stewart's theorem yields a relation between the lengths of the sides in the triangle to the length of its Cevian. And according to Stewart's theorem, the following equation is true: b squared times n plus c squared times n equals to a. We'll open brackets. Inside the brackets we have d squared plus m times n. Repeat again. In any triangle, b squared m plus c squared n equals to a. We open brackets. Inside the brackets we have d squared plus m times n. We'll prove that Stewart's theorem is true. That is to say that this equation is true in two different methods. In the first method, we start with the first method. In the first method, we'll do a construction. That is to say, from the vertex A, we'll draw perpendicular on BC. So, this angle equals to 90 degrees, and this angle, it is also equal to 90 degrees according to our construction. And we define the touching point of the perpendicular from point A and BC as E. We define the length of this line segment ED as X. We will define the length of line segment AE as H. What is the length of this line segment EC? The length of line segment EC equals to ED plus DC. ED plus DC. That is to say, EC equals to ED, that is X, plus DC, that is N. Therefore, EC in total equals to X plus N. X plus N. Likewise, what is the length of this line segment VE? From the drawing, it is very easy to see that here BE equals to BD minus DE. Okay, again, BE equals to BD minus ED. If I write it down, BE equals to BD minus BE. So minus ED. B equals to BD minus ED. So BE equals to BD equals to M units. So we substitute BD by M minus ED. ED equals to X units in length. So therefore we substitute ED by X. So in conclusion, we found out that BE, right segment BE equals to M minus X units in its length. Yeah. PE equals to M minus X units in its length. In the next step, we'll implement the Pythagoras theorem in the green triangle AED. Okay, so according to the Pythagoras theorem, the right green triangle AED, here by PT is the abbreviation for Pythagoras theorem. According to Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So the hypotenuse in the right green triangle AED is AD, therefore the square of the hypotenuse is AD square, and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AE square plus ED square. Repeat again, according to the Pythagoras theorem, in the right green triangle AED, AD square equals to AE square plus ED square. The hypotenuse AD equals to D units in its length, therefore AD square is D square, and it is equals to AE square. AE equals to H units in its length, therefore AE square is H square plus ED square. ED equals to X units in its length, therefore ED square is X square. In conclusion, we found out that according to Pythagoras theorem, in the right green triangle AED, D square equals to H square plus X square. In the next step, we'll implement the Pythagoras theorem in the right triangle AED. Again, by PT is the abbreviation for Pythagoras theorem. In the right green triangle AED, according to the Pythagoras theorem, AC square equals to EC square plus AE square. Repeat again, in the right triangle AEC, AC square equals to EC square plus AE square. Again, the right triangle triangle AED, AC square equals to EC square plus AE square. It's actually the right triangle AC. Repeat again, it is the right triangle AEC. Okay, here it is triangle AEC. Okay, this will be equation number 1. So according to equation number 1, AC square, AC is B, therefore AC square is B square equals to EC square. Here it is very easy to see that EC equals to x plus n, therefore EC square equals to x plus n square plus AE square. AE equals to h, therefore A square equals to h square. In conclusion, we found out that in the right triangle AC, according to the Pythagoras theorem, B square equals to x plus n square plus h square. We will open the brackets on this side of equation number 1, and we get that according to this equation number 1, B square equals to x plus n square equals to x square plus n square plus 2 times xn plus h square. So in this equation number 1, we have the expression x square plus h square. And we already found out that h square plus x square equals to d square. So we substitute h square plus h square plus x square by d square in this equation number 1, and we get here b square equals to x square plus h square is d square plus n square plus 2 times nx. So according to equation number 1, we found out that b square equals to d square plus n square plus 2 times nx. In the next step, we focus on the right triangle AEB, this right triangle AEB. Yeah. We'll focus on the right pink triangle AEB. And we'll implement the Pythagoras theorem on this right pink triangle AEB. In the right pink triangle AB by PT, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right pink triangle is AC, therefore the square of the hypotenuse, again the hypotenuse in the right pink triangle is side AB, therefore the square of the hypotenuse is AB squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AE squared plus BE squared. Repeat again. In the right pink triangle, triangle AB, according to the Pythagoras theorem, AB squared equals to AE squared plus AB squared. So AB equals to 0 in its length, therefore AB squared is C squared, and it is equals to AE squared. AE is H, therefore A squared is H squared plus BE squared. BE equals to A minus X unit in its length, therefore BE squared equals to A minus X squared. In conclusion, we found out that according to the Pythagoras theorem in the right pink triangle AEB, C squared equals to S squared plus M minus X squared. This is equation number 2. We'll open the brackets on this side of equation number 2 and we'll get that according to equation number 2. C squared equals to S squared plus M minus X squared. M minus X squared equals, according to the algebraic identity that A minus B squared equals to A squared plus B squared minus 2 times AB, we get that M minus X squared equals to M squared plus X squared minus 2 times M times X. So here we have this equation number 2, we have S squared plus X squared. We already found out that H squared plus X squared equals to D squared, therefore we substitute H squared plus X squared in this equation number 2 by D squared. And we get again that C squared equals to H squared plus X squared is D squared plus M squared minus 2 times mx. This is equation number 2, and we have already found out that according to equation number 1, b squared equals to d squared plus n squared plus 2 times n times x. In the next step, we create equation number 3 in the following way. In the first step, we multiply equation number 1 by m. In the next step, we'll multiply equation number 2 by n. And then we'll add the two equations with each other. This will give us equation number 3. Okay? So equation number 3 is created by multiplying equation number 1 by n, and then multiplying equation number 2 by n, and then adding the two equations with each other. We'll do it, create the equation number 3 in 2 steps. In the first step, we will multiply the right side of equation number 1. This is the right side of equation number 1 by m, which is m. Inside the brackets we have d squared plus n squared plus 2 times nx. In the next step we will multiply the right side of equation number 2 by n. This is the right side of equation number 2, so it will be n. Inside the brackets we will have d squared plus m squared minus 2 times mx. Okay, and it must be equal to the multiplication of the left side of equation number 1 by m. In the left side of equation number 1 we have b squared, so it is mb squared, plus the multiplication of the left side of equation number 2 by n. So in the left side of equation number 2 we have c squared, so it will be nc squared. Okay. So in the next step we will open the brackets in this side of equation number 3. And we get that according to this equation, equation number 3, m times d squared, here we open the brackets of this expression, so m times d squared is md squared plus m times n squared is mn squared plus m times 2nx is 2xmn. We'll also open the brackets of this expression and we get that n times d squared is nd squared plus n times m squared is nm squared. N times minus 2mx equals to minus 2xmn. And it must be equal to, on the other side of the equation number 2 we have mb squared plus nc squared. So actually this is equation number 3 after we open the brackets. In this equation number 3, we have plus 2xmn minus 2xmn is 0. So those two expressions will get cancelled. And what is left from equation number 3 after the two expressions cancelled? We have here md squared plus mn squared plus nd squared plus nm squared equals to mb squared plus nc squared. In the next step, we take out this square as a common factor from md squared and also from nd squared. So what is left from md squared after we took from d squared as a common factor? What is left is actually m. And what is left from nd squared after we took from it n, after we took from it d squared as a common factor? What is left is actually n. Plus we also take a common factor of m times n from nm squared and also from nm squared. So what is left from nm squared after we took from it nm as a common factor? What is left is actually m plus what is left from mn squared after we took from it mn as a common factor. What is left is actually n, and it is equal to mb squared plus nc squared. In the next step, we'll take out m plus n as a common factor from those two expressions. So we get here m plus n is taken out as a common factor. So what is left from d squared times m plus n after we took from it d squared as a common factor? What is left is actually d squared plus what is left from m plus n times mn after we took from it mn as a common, n plus n as a common factor. What is left is actually mn, and it is equals to b square m plus c square n. Here m plus n equals to a. It is very easy to see it in the drawing. Here we have in the original drawing, from one side BC equals to A, from the other side BC equals to BD plus DC. That is to say BD equals to BC equals to BD, that is n, plus DC, that is n. So BC in total equals to m plus n from one side, from the other side BC equals to A, therefore m plus n equals to A. Okay, m plus n equals to A. So we substitute m plus n in this equation, equation number 3, by A, and we'll get that here m plus n is A. Inside the brackets we have d squared plus m times n equals to b squared m plus c squared n. Okay, and this is exactly Stewart's theorem. So we proved Stewart's theorem in the first method. In the next step, I'll show you how we can prove Stewart's theorem or the Stewart's equation in a different method. So we prove Stewart's theorem in a second method. In the second method, we define this angle ADB as theta. Therefore, the adjacent angle ADC, this angle must be equal to 180 degrees minus theta, according to rule number 1, that the sum of the angles from one side of a straight line is equal to 180 degrees. BC is a straight line, therefore if we focus on the upper side of BC at point D, the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have at the upper side of BC at point D? We have this angle theta plus the missing angle. In total it must be equal to 180 degrees. Therefore the missing angle must be equal to 180 degrees minus theta. Why? Because 180 degrees minus theta plus theta is 180 degrees, exactly according to rule number 1. Okay, so in the next step we will implement the law of cosines in the green triangle, triangle ABD, and also in the pink triangle, this is the pink triangle, triangle ADC. I remind to you quickly what is the law of cosines. Actually, the law of cosines is true in any triangle. So this is triangle ABC. that could be any triangle. The length of side AB is A units, side AC equals to B units in its length, and finally side BC equals to C units in its length, and this angle BAC equals to theta. Then according to the law of cosines, the following equation is true. That C square equals to A square plus B square minus 2 times A times B times cosine theta. Again, C square equals to A square plus B square minus 2 times A times B times cosine theta. Here we will add 2 times AB cosine theta to this equation, and we'll get that C square plus 2 times AB cosine theta equals to A square plus B square. In the next step, we subtract C square from this equation, and we get that 2 times AB cosine theta equals to A square plus B square minus C square. In the next step, we will divide this equation by 2 times AB, and we'll get finally that cosine theta equals to A square plus B square minus C square over 2 times AB. In the next step, we'll implement the law of cosines in the green triangle ABD. So in the green triangle ABD, according to the law of cosines, we'll get that cosine theta equals to D squared plus A squared minus C squared over 2 times D times M. So actually, this equation number 1, cosine theta equals to D squared plus A squared minus C squared over 2 times D times M, is the implementation of the law of cosines in the green triangle ABD. In the next step, we will implement the same law, the law of cosines, in the pink triangle ADC. According to the law of cosines, in the pink triangle ADC, cosine 180 degrees minus theta equals to D squared plus N squared minus B squared over 2 times D times N. So cosine theta equals to D squared plus N squared minus B squared over 2 times D times N. This equation number 2, is the implementation of the law of cosines in the pink triangle ADC. Triangle ADC. The pink triangle ADC. So if cosine 180 degrees minus theta equals to minus cosine theta. Okay. Write it down. Cosine, according to the trigonometric identity, cosine 180 degrees minus theta is equal to minus cosine theta so we will substitute cosine 180 degrees in this equation number 2 by minus cosine theta. Again, we'll substitute cosine 180 degrees in this equation number 2 by minus cosine theta. And here it is equals to d square plus n square minus b square over 2 times d times n. Okay. The next step, we will multiply this equation number 1 by minus 1, and we will get that according to this equation number 1, cosine theta equals to minus cosine theta, and here we multiply also, of course, this side also by minus 1, so it will be minus 1. Here we make brackets. Inside the brackets we have d square plus a square minus 3c square over 2 times d times m. So we have two different expressions for minus cosine theta. Therefore, we'll create the equation number 3 that states that minus cosine theta, according to equation number 1, must be equal to minus cosine theta according to equation number 2. Very simple. Okay? So here, minus cosine theta according to equation number 1 equals to minus d square plus a square minus c square over 2 times d times m, and it must be equal to minus cosine theta according to equation number 2 minus cosine theta according to equation number 2 equals to d square plus n square minus b square over 2 times d times n. In the next step, we multiply this equation number 3 by 2d. So, on this side, we multiply this side by 2d, so 2d over 2d is 1, so 2d will get cancelled. So in the denominator of this side of equation number 3, we left only with m. The numerator didn't change. The numerator stays as minus d square plus a square minus c square. And it must be equal to, we multiply those, of course, this side by 2d. So 2d over 2d is 1, 2d will get cancelled. So in the denominator of this side of equation number 3, we left only with n. The numerator didn't change. The numerator stays as d square plus n square minus b square. In the next step we multiply this equation, we cross multiply this equation, equation number 3, and we get that according to equation number 3, we have here minus n, inside the brackets we have d squared plus a squared minus c squared equals to m d squared plus n squared minus b squared. In the next step, we'll open the brackets on both sides of this equation, equation number 3, and we'll get that according to equation number 3, minus n times d squared is minus n d squared, minus n times a squared is minus n a squared, actually here it is m actually. It is not a but m. This side of the green triangle is m. So it is d squared cosine theta equals to d squared plus m squared minus c squared. Okay? It is not a by m. It is not a but m. So it is d squared plus m squared. So minus n times m squared is minus nm squared, and minus n times minus c squared equals to plus nc squared. Why? Because minus times minus is plus, equals to m times d squared is md squared, plus m times n squared is mn squared, plus m times b squared equals to mb squared. Okay. In the next step, we add to this equation, equation number 3, nd squared. So here nd squared minus nd squared is 0. In the next step, we'll add also nm squared to this equation number 3. So nm squared minus nm squared is 0. And finally, we'll subtract from this equation, equation number 3, nc squared. So nc squared minus nc squared is 0. So in total, in this side of the equation, we left with nothing, with 0. We'll do the same operation also on the other side, of course, of equation number of this equation number 3. So in this side of equation number 3, we have already had the expression md squared plus mn squared plus mb squared. We have to add to this side of equation number 3 nd squared, and we also have to add to this side of equation number 3 nm squared, and finally we have to subtract from this side of equation number 3 nc squared. So this is minus nc squared. Okay. In the next step, we take out d squared as a common factor from md squared and also from nd squared. So what is left from md squared after we took from it d squared as a common factor? What is left is actually m plus nd squared. What is left from nd squared after we took from it d squared as a common factor? What is left is actually n, and we'll also take out mn as a common factor from this expression and also from this expression. So what is left from nm squared after we took from it nm as a common factor? What is left is actually m plus mn squared. What is left from mn squared after we took from it mn as a common factor? What is left is actually n. And it is equal to here it is minus mb square equal minus mb square minus nc square equals to 0. Here, this expression is minus mb square. It is actually, we have here m times minus b square, m times minus b square, repeat again, m times minus b square equals to minus mb square. It is minus mb square, here also minus mb square, minus nc square equals to 0. In the next step we will add to this equation, equation number 3, mb square and also mc square. And we get that according to this equation, equation number 3, d square m plus n plus mn m plus n equals to mb square plus mc square. Okay, in the next step we take m plus n out as a common factor from those two expressions. So what is left from d square times m plus n, after to prove it m plus n is a common factor, what is left is actually d square plus what is left from m plus n times mn, after to prove it m plus n as a common factor, what is left is actually mn, and it is equal to b square m plus d square m plus c square n. In the next step, we have already found out that m plus n equals to a in the first method, so we substitute m plus n by a in this equation, equation number 3, and we'll get that according to this equation, equation number 3, m plus n is a. Inside the bracket we will have d square plus mn equals to b square m plus c square n. Okay. A d square plus mn equals to b square m plus c square n, and this is exactly Stewart's theorem. So we prove Stewart's theorem according to the second method. In the next step, I'll summarize the lecture. We'll start with the first method, of course. So in this lecture, we proved Stewart's theorem in two different methods. In a nutshell, Stewart's theorem yields a relation between the lengths of the sides on a triangle to the length of its area. Again, Stewart's theorem yields a relation between the lengths of the sides of the triangle, the length of the sides in the triangle, to the length of its civilian. The civilian here is AD. It's equal to the units in its length. Okay, here in this triangle ABC, that could be any triangle, the length of side AB is units, side BC equals to A units in its length, side AC equals to B units in its length. In addition, also line segment BD equals to N units in its length, line segment DC equals to N units, and the civilian in this triangle ABC is AD, that is equal to the units in its length. And according to Stewart's theorem, the following equation is true. B squared times M plus C squared times N equals to A, open brackets, inside the brackets we have D squared plus M times N. Okay, B squared M plus C squared N equals to A, we open brackets, inside the brackets we have D squared plus M times N. We prove that this equation is true in two different methods. In the first method, we did the construction. That is to say, from point A, we draw perpendicular on BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in BC as M. Okay, then we define the touching point of the perpendicular from point A in BC as E. So here, then we define line segment ED as X, we define line segment AE, this line segment as H, line segment EC equals to X plus N, and this line segment BE equals to BD minus ED, that is to say it is M minus X. Then we implemented the Pythagoras theorem on the green right triangle AED. The green right triangle, according to the Pythagoras theorem, AD square equals to AE square plus ED square. Repeat again, in the right green triangle AD, according to the Pythagoras theorem, AD square equals to AE square plus ED square. Okay, here AD equals to the units, therefore AD square is D square. AE equals to H, therefore AE square is H square, and MD equals to X, therefore MD square is X square. So in conclusion, found out that according to the Pythagoras theorem, D square equals to H square plus X square. Then we focused on the right triangle AEC, and we implemented the Pythagoras theorem in the right triangle AEC. According to the Pythagoras theorem in the right triangle AEC, AC square equals to AE square plus MC square. Repeat again, in the right green, this partial green, in the right triangle AEC by PT, AC square equals to EC square plus AE square. Here, EC equals to X plus N, AM equals to H, and AC equals to B. Therefore, according to the Pythagoras theorem, we get that B square equals to X plus N square plus H square. We open the brackets on this side of equation number 1 and found out that according to equation number 1, B square equals to X square plus N square plus 2 times Xn plus H square. We already found out that H square plus X square equals to D square, therefore we substituted H square plus X square in this equation number 1 by D square. And we found out that here B square equals to X square plus H square is D square plus N square plus 2 times NX. So this is equation number 1. Then we created equation number 2 by implementing the Pythagoras theorem on the right pin triangle AEB. On the right pin triangle AEB by PT, AB square equals to AE square plus EB square. Repeat again, AB square equals to AE square plus BE square. Okay, so AB equals to C units in its length. AE equals to H units in its length. And finally, EC equals to m minus x units in length. Therefore, we get that according to Pythagoras theorem, c squared equals to h squared plus m minus x squared. We open the brackets of this side of equation number 2 and found out that c squared equals to h squared plus m minus x squared equals to m squared plus x squared minus 2 times mx, according to the algebraic identity that a minus b squared equals to a squared plus b squared minus 2 times ab. Here again we have h squared plus x squared that is equal to d squared according to this equation. Therefore we substitute h squared plus x squared by d squared in this equation number 2, and found out that c squared equals to h squared plus x squared that is d squared plus m squared minus 2 times mx. This is equation number 2, and we have already found out that according to equation number 1, b squared equals to d squared plus n squared plus 2 times nx. Then we created equation number 3 in the following way. We multiplied the equation number 1 by n. Then we multiplied the equation number 2 by n, and then we added the two equations with each other. This created the equation number 3. So we did it in 2 steps. In the first step, we multiplied the right side of equation number 1, this is the right side, by m. This is the right side of equation number 1, so it is m. Inside the brackets we have d squared plus n squared plus 2 times nx. In the next step we multiply the right side of equation number 2 by n. This is the right side of equation number 2, so it is n. Inside the brackets we have d squared plus m squared minus 2 times mx, and it must be equal to the multiplication of the left side of equation number 1 by m, so it is mb squared plus the multiplication of the left side of equation number 2 by n, so it is nc squared. Okay. We open the brackets on this side of equation number 3. Here, m times d squared is md squared. M times n squared is mn squared, plus m times 2nx is 2xmn. We opened also the brackets of this expression. N times d squared equals to nd squared, n times n squared equals to nm squared, and finally n times minus 2mx equals to minus 2xmn, and it is equal to mb squared plus nc squared. So actually this is equation number 3 after we open the brackets. In this equation number 3 we have, in this side of equation number 3 we have plus 2xmn minus 2xmn is 0. So those two expressions we get cancelled. So after we cancel the two expressions, what is left from equation number 3? What is left is actually mb squared plus mn squared plus nd squared plus nm squared equals to mb squared plus nc squared. Then we took out this square second factor from nd squared and also from md squared. So inside the brackets, what is left is actually m plus n. Then we took out the common factor mn from mn squared and also from nm squared. So inside the brackets we left only with m plus n. And it must be equal to mb squared plus nc squared. Then we took out m plus n as a common factor from those two expressions. So inside the brackets we left only with d squared plus mn, and it is equal to b squared m plus c squared n. Then m plus n equals to a. It is very easy to see from the drawing that m plus n equals to a, well, because side BC from one side equals to a units. From the other side, side BC equals to m plus n, therefore m plus n equals to a. So we substituted m plus n by a in this equation number 3, and found out that according to equation number 3, m plus n is a. Inside the brackets we have d squared plus mn equals to b squared m plus c squared n. And this equation is exactly Stewart's equation, Stewart's theorem. So we proved Stewart's theorem in the first method. Then I presented to you how to prove Stewart's theorem in the second method. In the second method, we defined this angle ADC as theta, therefore the adjacent angle this angle is angle ADB. We defined it as theta, therefore the adjacent angle ADC must be equal to 180 degrees minus theta, according to the rule that the sum of the angles from one side of a straight line is equal to 180 degrees. Then we implemented the law of cosines in the green triangle and then also in the pink triangle. What is the law of cosines? The law of cosines is true in any triangle. This triangle ABC could be any triangle. The length of side AB is a unit, side AC equals to B units in its length, and finally side BC equals to C units in its length. And this angle BAC equals to theta. And according to the law of cosines, in this triangle ABC that could be any triangle, the following equation is true: that C square equals to A square plus B square minus 2 times A times B times cosine theta. Again, C square equals to A square plus B square minus 2 times A times B times cosine theta. If we had to do this equation 2 times AB cosine theta, then we'll subtract C square and then we divide it by 2 times AB, we'll get that cosine theta equals to A square plus B square minus C square over 2 times AB. So we implemented this law, the law of cosines, in the green triangle, triangle ABD. The green triangle, triangle ABD, according to the law of cosines, we get that cosine theta equals to A square plus D square. Again, cosine theta equals to side DB equals to N. So cosine theta equals to D square plus M square minus C square over 2 times D times M. Repeat again, cosine theta equals to D square plus M square minus C square over 2 times D times M. Repeat again, in the green triangle, triangle ADB, cosine theta equals to D square plus M square minus C square over 2 times D times M. Likewise, we implemented the law of cosines in the pink triangle, triangle ADC. In the pink triangle, triangle ADC, according to the law of cosines, cosine 180 degrees minus theta equals to D square plus N square minus B square over 2 times D times N. Repeat again, the pink triangle, triangle ADC, cosine theta equals to D square plus N square minus B square over 2 times D times N. We have the trigonometric identity that cosine 180 degrees minus theta equals to minus cosine theta. Therefore, we can substitute cosine 180 degrees minus theta by cosine theta. We did it and we got that minus cosine theta in this in equation number 2 equals to D square plus N square minus B square over 2 times D times N. Then we multiply this equation number 1 by minus 1. So minus 1 times cosine theta equals to minus cosine theta, and it is equals to minus, we put this expression in brackets. Inside the brackets we have D square plus M square minus C square, all divided by 2 times D times M. So we have 2 different expressions for minus cosine theta, and therefore we get the equation number 3 that states that minus cosine theta according to equation number 1 must be equal to minus cosine theta according to equation number 2. Minus cosine theta according to equation number 1 equals to D square plus M square, D square plus M square, D square plus M square minus C square over 2 times dm. And it must be equal to minus cosine theta according to equation number 2. Minus cosine theta according to equation number 2 equals to D square plus N square minus B square over 2 times D times N. In the next step we multiplied this equation number 3 by 2d. So here 2d over 2d is 1, so 2d we can cancel, so in the denominator we left only with m, the numerator didn't change. Then we multiplied also this side by 2d. 2d over 2d is 1, so in the denominator we left with n, the numerator didn't change. So actually got this expression after multiplied by 2d, equation number 3 by 2d. Then we cross multiplied this equation and we found out that m d square plus n square minus b square equals to minus n d square plus m square minus c square. Then we open the brackets on both sides of this equation number 3, and we found out that minus m times d square is minus n d square, minus m times m square is minus n m square, minus n times minus c square equals to plus n c square, because minus times minus is plus. We open the brackets also here. M times d square is m d square, m times n square is m n square, and finally m times minus d square equals to minus mb square. Minus mb square. Then we added to this equation number 3, n d square. So here n d square minus n d square is 0. Then we added mb square and m square. So nm square minus nm square minus nm square is 0. And finally we subtracted nc square. So nc square minus nc square is 0. So in this side of the equation we left with 0, nothing. Then we did the same operation, of course, on the other side of equation number 3. In the equation number 3, we already had the expression m d square plus n m square plus minus mb square. So we have to add to this equation, to this side of equation number 3, mb square. We have to add also n d square, and we have to add to this equation number 3 n d square, and also we have to add here n m square, and we have to subtract n c square. So this is equation number 3 after we did this operation. Then we took this square as a common factor out from md square and also from nd square. So inside the brackets we have m plus n. Then we took mn as a common factor from nm square and also from mn square and also from nm square and also from mn square. Inside the brackets we left only with m plus n minus mb square minus nd square equals to 0. We added to this equation number 3, mb square and also nc square. So here in this side of the equation, mb square and mc square will get cancelled. Inside of the equation we have before that 0. So here after the operation we will have mb square plus nc square. So we found out that this square m plus n plus mn m plus n equals to mb square plus nc square. Then we took m plus n, we took out m plus n as a common factor from those two expressions. So inside the brackets we left only with d square plus mn equals to b square m plus c square n. And then here m plus n, we already found out that m plus n equals to a we only found out that m plus n equals to a. Therefore we substitute m plus n by a, and finally we found out that m plus n is a. Inside the brackets we have d square plus mn equals to b square m plus c square n. Again, found out that a d square, inside the bracket we have d square plus mn equals to b square m plus c square n. And this is exactly Stewart's theorem. So we succeeded to prove Stewart's theorem in two different methods. Okay, thank you very much.